All right, so welcome back to the last session for tonight. Glad you are all here. So we will begin with a very interesting talk by Anasasia Pustozerova about federated learning, present and future of privacy in AI. So Anastasia, she's a researcher at SBA Research and also does her PhD at the Technical University of Vienna. And definitely, if you ask our master students, she's one of the favorite lecturers here in our Master Data Intelligence. So, floor is yours.
Thank you very much for a nice introduction. Yeah, today we'll talk about federated learning, present and future of privacy in AI, and how federated learning is involved in it. So first, I actually want to ask who of you has ever heard about federated learning? Okay, quite a few. Who of you has ever worked with federated learning already? Okay, remember these people, you can use it for the lottery later, also me. But I'm sure everyone will learn something new today, maybe besides my supervisor, but otherwise let's get going. So we're talking about machine learning, and we see it ever in many industries, and machine learning requires a lot of data. Data collection, however, can be a very tedious process. You might ask your colleagues, so you probably have already experienced that data collection is not that easy task. And it's for a reason, because data usually contains private or sensitive information. And collecting such data brings a lot of bureaucracy and legal responsibilities. Leakage or unauthorized access to the data poses threats to data owners, and also might result in a very big fines if you're a company who leaked the data due to GDPR. So federated learning essentially helps us to tackle this problem. And how, I will show you now. So in classical or centralized machine learning, the training goes in the following way. Imagine that we have our data distributed in a different clients. In this example, it could be medical institutions who have patients' data, and they want to train machine learning model which predicts, let's say, lung cancer, and it needs a lot of data to create better models. So in centralized machine learning, the data is aggregated at the server, and then, based on this data, we train our machine learning model. However, as you may guess, there's a very big threat that private data can leak from the server or can be misused if the server is malicious. And federated learning suggests us a pretty straightforward solution. You can't have data loss in the cloud if you don't put your data in the cloud. So in federated learning, our data stays at a hospital. But each hospital or federated learning client trains machine learning model locally, and then sends this locally trained model to the server, which then already aggregates all these different locally trained models into the global model. This global model is a resulting model of federated learning and should give you good predictions on your lung cancer, and can be further distributed for further research or to other medical institutions. Or it can be sent back for following optimization. For instance, if you use some stochastic gradient descent or other optimization approach, you can optimize your global model for several federated learning iterations. So this is it, federated learning. A server collects machine learning models instead of private and sensitive data. Federated learning is already actually used by Google and Apple for mobile keyboard prediction, for instance. Next word prediction for Hey Siri. It also very popular in IoT domain, and of course medical domain, because you have case of very sensitive data. It's used for pharmaceutical discovery or research on health data. I personally work at a project which is called Feature Cloud, where we built a solution based on federated learning, allowing researchers to process private patients' data in a secure and private way. Federated learning allows to train data in a private way, and it's super nice and easy, straightforward solution. However, it poses a few challenges. One of them is communication costs. Sometimes you need to, as I already showed before, you need to do several iterations of communication to train a better global model. Sometimes you have too many clients which you need to collect models from, and your communication costs might be too high. And in this case, you might use some client sampling or other methods to reduce the communication costs. Another problem is the data or system heterogeneity, that data which originates in different devices can be a different distribution, which may also cause difficulty when you try to train your global model, so it might take more federated iterations to converge. Another problem in federated learning is security risks. If you have some of the client's malicious user, they may try to intrude federated learning process or corrupt it to perform misclassification of the final global model. And the last but not least problem of federated learning, where my personal research is focused on, is privacy risks. And as you may guess, the privacy risks in federated learning arise from the models, because we don't need to transfer data, but we transfer models. And models, they are an abstraction of our training data. And there are ways how you can extract sensitive information about training data just having access to the model. So one of this, few of these approaches are called inference attacks. You can perform inference attacks on machine learning models to infer some sensitive information. It can be in the form of attribute inference, where you try to infer a known attribute having access to the model. It can be in the form of model inversion. Here you have an example of the original data sample and the sample which was recreated, just having access to the machine learning model. So it was recreated from the machine learning model. And another very popular attack, inference attack on machine learning model, is membership inference. And the goal of membership inference is to find out if any particular instance was in the training set of the model, which can be itself already sensitive information. So let's go back to our federated learning setting and imagine what could be the threats arising here from the inference attacks. So first of all, we can have the malicious server. Malicious server has access to all the locally trained model and may try to infer from this model information about private patients' data. Another attack scenario we're considering is a malicious client. When the client has an access to the global model, he or she may try to infer sensitive information about training data from other clients having access to this global model. The last case, which we consider in federated learning, is the malicious users of final global model. And, when we train our global model, it can be further distributed to other parties or other medical institutions for prediction. And users of this final global model can also try to infer sensitive information about original training data. There are several mitigation strategies one can use to protect from these risks. For example, for malicious server, one can utilize homomorphic encryption, secure multi-party computation, or differential privacy. If you're more interested in this strange words, we can talk later. But now we'll focus on differential privacy, because as you can see, it's also an approach which allows us to secure from malicious client and malicious users of final global model. So differential privacy is essentially a way to add noise to your data or to your model to make your model private. You can add this noise either to your input in the form of input perturbation. This noise can be added during training to the objective function or to the gradients if you have gradient optimization, for instance. And the last place where differential privacy can be applied, it's at the output. It's on already trained model. It's called output perturbation. So it's applied on the trained model's weights. These are results from my last paper, which now submitted for a conference. Please don't copy, not accepted yet. So I was looking at two different approaches, gradient perturbation and output perturbation, to preserve privacy in federated learning. Here on the plot, you can see the parameter epsilon. which basically says us how private is the model. The lower the epsilon, the more private the model is. And you can see that here privacy loss, which is dashed line, is very low, so we don't have privacy loss. However, at the same time, we have very, very high utility loss. So that means that our model performs like 60% worse than it was initially. So in this case, our model is totally ruined and useless. Therefore, you can see that privacy is always a trade-off between privacy and actually utility of the model. And in this case, for instance, when we're ready to sacrifice 5% of our model accuracy, we can achieve privacy loss also of only 5%. And in this case, we can see that output perturbation, for instance, performs better than gradient perturbation and allows us for better trade-off. Another important insight from this research was that output perturbation allows for the global model to converge with fewer federated learning iterations. Therefore, it's also more communication efficient because you don't need to do several cycles of federated training. So to conclude, federated learning is cool, and it allows to train machine learning models on distributed data without sharing private data and transferring only machine learning models. However, federated learning still poses few challenges like communication costs, data and system heterogeneity, security, and privacy risks. Privacy risks in federated learning can be mitigated by different methods like secure multi-party computation, homomorphic encryption, or differential privacy. However, differential privacy always suggests you a trade-off between privacy and model's utility. If you want to learn more about privacy-preserving machine learning, federated learning, or differential privacy, feel free to talk to me later, and I'm ready also to answer any of your questions now. Thank you for your attention. Oh, we have one. Nice.
Thank you. It's very interesting. So, as you said, you're working on it on a research level. Mm-hmm. Are there already open source libraries that are ready to use to?
Yes, there are quite a few. I could recommend you TensorFlow Federated. If you're a fan of TensorFlow, there is also there is also a framework which is called Flower. And if you're a fan of PyTorch, there's a framework which is called PySift. Yep. So there are a few, and of course you can find on the internet. So also this Feature Cloud platform, which I was talking before, you can actually also try to build your federated learning model there. So check out featurecloud.eu, I think, or .ai. So you can also try to build your federated learning model there.
Thank you.
Thanks, first of all, for a very interesting talk. And sorry if my question is super naive. You mentioned earlier that there were like regulations from the I guess European Union.
Yeah.
Are there also regulations on how? I don't know. I imagine if that model you get basically is super simple, then you can extract a lot from the original data. So is that even? Are there no regulations yet, and why this is used, or is it? Is there like a minimum complexity it has to have? Because neural networks suffer from very low explainability, and this is what you use here basically. So if the less explainable is, the better. But I wonder if there are some regulations or something.
I am not sure about legal regulations, but we're working on this Feature Cloud project, which is also financed by the European Union. And there, one of our targets is actually to ensure the privacy in federated learning, because we know that there are threats of leakage from the model. And as you said, the simpler the model, the easier the leakage. This is why, in our project, we're really tackling this problem, and we're using additional privacy-enhancing technologies to ensure privacy. But as you said, like that from the neural networks, for instance, it's like black box. Even from neural networks, you can leak the data, and this is also what am I doing in my research. This is also a problem, and it's being tackled in research. But I'm really not sure how it's actually legally, what are the legal side of this?
Maybe a slight follow-up question. You also mentioned you can always just add noise, but okay, if you increase too much noise, then it's completely different data. And explaining is the question is, do you see much more effectiveness if you use little noise but very complicated pre-trained models, or vice versa?
This is actually a very good question. It's also part of my future research, compare how this differential privacy actually performs on different type of models, because here actually the results for logistic regression, pretty simple model. And you can see that when you add a lot of noise, the model is ruined. It is interesting how it will be in comparison to neural networks, for instance. Yeah, this is ongoing research. I didn't meet an evaluation like comparing like this, based on the different machine learning models. This is exactly what I'm planning to do next. So yeah, maybe I will be able to answer your question then.
Thanks.
Small question for me. Isn't the risk of data leakage smaller if the model is more complex? I mean, if you have a big neural network, isn't the risk of data leakage of single samples pretty small?
Actually, I did some experimental evaluation on this topic, and I got opposite results because the bigger neural networks, they actually able to remember better your data.
Okay, so the more generalized the model is, the less is the risk of leakage.
Yes, but there is exactly this connection with generalization. If your model generalizes well, it leaks less data. If it overfits more, it leaks a lot of data. Yeah.
I mean, mostly you want to generalize, but not in cases of large language models. Also.
Exactly. So there are like some specific cases where you want to train like quite model fit into particular data set.
Okay, one question we had over here, and then.
Okay, so thank you for the presentation. I have a small question. So let's say that I'm a malicious client, and I'm joining a network where there are more than 10 clients working together to create federated learning models. Now, of course, even with the differential privacy, the aggregated model should be better than my locally trained model because there's more data to it. So my question is, what's there to stop me from joining, let's say, the network, getting the aggregated model, the super complex model, and then just leaving the network?
You mean that you will get your model and then you will not participate in the training model?
Yeah.
I mean, I don't think there is a difference if you just leave the network right away, or you keep on using it and still use your model in malicious purposes. So the case here in general, we want to prevent anyone from the malicious usage of the models. And by introducing, for instance, differential privacy, you already will be able to infer less information, like even if you're a malicious user and you want to infer sensitive information from the global model. So here, we use this differential privacy exactly to secure from the leakage of the global model too.
Okay, thank you.
Okay, one last question back there.
Thank you for the talk, really interesting. I was wondering, maybe it's a noob question, but how do you merge the local models into a bigger model?
Thanks, very good question. Because, very essential for all federated learning. There are different aggregation techniques depending on which models you have. For instance, for decision trees, sometimes they just accumulate all the trees together and use it as a random forest. For neural networks or for logistic regression, it's usually average of the weights. So you take weights of your model, and for neural networks, as you might guess, you need to agree on architecture beforehand. This is why federated learning usually starts with a server randomly initializing global model. then send it to everyone. So everyone has this same model with the same architecture with random weights, and then they start training already from this point together. And then it's also faster convergence because they start from the same point.
Cool, thanks.
Yeah, you're welcome.
Okay, thank you very much, Anastasia.
Thank you.
As
Thank you for your
always,
questions.
it's a pleasure having you here. And also for you, we have this our little present.
Thank you so much.
Okay, thank you very much.